Welcome back. This is a continuation of the previous video. We're working on applying the continuous time Fourier transform to differential equations. So let's continue on. Now, from the last video, we started with this differential equation up here in the top right. And from it, we were able to deduce a frequency response that was in this form. And then we use partial fraction expansion to get it into these two pieces, which I've boxed here. And then, so that's really the frequency response. And then we took it a little bit further and we got the inverse transform and we got the impulse response of the system. And here is the common Fourier transform pair that we used to get the inverse transform. So again, this differential equation is characterizing a linear time-invariant system. It's characterizing this frequency response, and it's characterizing this impulse response. That's where we're at. Now, we're going to take this one step further, and we're going to say, suppose now the input to the system is x of t equals, and we're going to say e to the negative t u of t. Now, that might sound contrived or textbook, but this is the kind of signal you get from like a decaying RC circuit. The circuit doesn't decay, the capacitor decays in an RC circuit. So this signal could be coming from a resistive capacitive circuit, and it's also nice that we have the Fourier transform of this thing right there ready to go. So the goal here now, given x of t, given the differential equation, find the output. Find the output, y of t. Okay, so let us do that. Well, we're going to use Fourier transforms, and I want to be clear that what we could do is convolve x with h, little h. We could do that convolution, and if we did that convolution, we would certainly have the output. You can always convolve x with h and get the output. However, we're going to use Fourier transforms, and the convolution property says that the convolution of x with h is the multiplication of capital X with capital H. That gives us the Fourier transform of the output. Okay, so we've got capital H, and we can easily get capital X. Let's do that by using this Fourier transform pair. So e to the negative t, a is 1, u of t. Then this has a Fourier transform 1 over j omega plus 1, like that. So now we have x, capital, and we have h, capital. So let's multiply them together. So y of j omega equals x of j omega times h of j omega. So that's equal to 1 over j omega plus 1 times, and I'm going to use this form of h before we use partial fraction expansion. You'll see why in just a second. Hint, I'm going to need to expand it again, so I'm backing up from the expansion. So now notice that we have, when we do the multiplication, we have a common term there. So we can write this multiplication like this: j omega plus 2 over j omega plus 1 squared times j omega plus 3. And it's this now that we have to expand. We have the Fourier transform of the output y, but we need to expand it so that we can get the signal y. That's what we're looking for. So this is a new case now for us. This is a new mathematical case for us because we have a term that's repeated in the denominator. We have j omega plus 1 squared. And I don't really want to go into why, but you should have learned in your math course the form of the expansion is going to be j omega plus 1, some constant over that, plus some constant over j omega plus 1 squared, plus some constant times or over j omega plus 3. This is the form of the expansion, and we have to get constants a, b, and c. Now, we're going to run into a small issue with getting a, which is the repeated root, when you use my method. All right, and we'll get to that in a second, but let's use my method to get b and c. So we're actually going to make an amendment to my method here just to get this repeated root. But we can get b and c as we always do. So let's get b. To get b, I'm going to multiply this thing in orange. Multiply that thing in orange by b's denominator and set j omega equal to whatever makes b's denominator 0. So let's do that. So I multiply by b's denominator, and then on the left I would have j omega plus 2 over j omega plus 3 equals, I'm going to write all of this out, but as you're getting more and more comfortable with this, you might find that you really don't have to write this stuff out, which is amazing once you get to that point. Plus b, right? Plus c times j omega plus 1 squared over j omega plus 3. And notice for a, you could cancel one of these, so let's do that. Let's cancel that with one of these guys. Okay, now I'm going to strategically let j omega equal minus 1. So then for b, I have b equals, right, because now this drops out, 0, this drops out, 0, so b equals minus 1 plus 2 over minus 1 plus 3, and so this is 1 over 2, 1/2. Awesome. So I can update my equation if I wanted to, but I'll leave it for right now. I'll leave it as 1/2, and I'm going to create some space. So I'm going to delete this. Feel free to pause the video if you need to copy some of this stuff down, but I'm moving on. Okay, so I'm going to use this space up here. Now I've got b. I'm going to get c in the exact same way. So I'm going to multiply everything in orange by c's denominator, and then let j omega equal to whatever makes c's denominator 0, which is minus 3. So when I do this, let's try to do it in our head, actually. So I'm going to have c equals, so imagine multiplying everything by j omega plus 3, and then setting j omega equal to minus 3. On the right, I would have c equals, and then on the left, I would have minus 3 plus 2 over minus 3 plus 1 squared. Right? And so this is minus 1 over minus 2 squared, which is 4. So it looks like, to me, c is minus 1/4. See that? It's pretty nice once you get used to that. So just as you're getting used to it, I'm gonna change it up a little bit. I'm gonna amend to the process. And so notice if we try to get a, let's try the method on a. So multiply by a's denominator. So when I do that, when I multiply by a's denominator, I would have j omega plus 2, and then one of these would cancel, j omega plus 1 times j omega plus 3 equals a, and then notice b. One of them cancels with b, like that, but not both. Okay, and so when I let j omega equal to minus 1, I have a problem here because of the repeated root. See, I've got this issue, and so I'm not going to be able to do that. That's why I have a problem with a. So let's back up a little bit. So what we can do instead is multiply. So this is what we're going to do. We're going to multiply by the repeated root first. So I'm going to multiply by j omega plus 1 squared, everything. So this gives me j omega plus 2 over j omega plus 3 equals a times j omega plus 1, right? Because I'm multiplying by the repeated root, j omega plus 1 squared. So that gives me a times j omega plus 1 plus b plus c times j omega plus 1 squared over j omega plus 3. I'm writing all of this out, but you'll see that you don't have to write all this out once you get used to it, that things are going to cancel just like they did before. All right, so now, and here's the trick, and this is not well received among students at first, but once you work with it, you'll get the hang of it. I'm going to take the derivative with respect to j omega of this thing. All right, so when I take the derivative on the left, and I'm going to consider peanut butter and jelly, so I'm considering j omega as the variable. On the left, I have the bottom times the derivative of the top, which is 1, minus the top times the derivative of the bottom, which is 1, over the bottom squared. Okay, and the j omegas would cancel. And then I would have 1 in the numerator equals, and then let me take the derivative of the right, so j versus j omega, so I have a times j omega, so that leaves me with just a. That's nice. B gets wiped out because it's a constant, so that's nice too. And then C is a little bit messy. I'm going to write it out though, but you're going to see that C is going to cancel eventually. But let's write it out. But notice that B was the problem in this because B had the repeated root. B was the problem, but B's wiped out now. So taking the derivative wiped out B. So now the bottom times the derivative of the top. So the bottom is j omega plus 3 times the derivative of the top, which is 2 times j omega plus 1, minus the top, j omega plus 1 squared times the derivative of the bottom is 1 all over the bottom squared. That looks messy, right? But now I'm going to strategically let j omega equal minus 1, which was the thing in A's denominator that made the denominator equal 0. So when I do that, this term goes away, this term goes away, so the contribution to C goes away completely. That's why you don't really even have to write this out. And you get A equals 1 over, and then you plug in minus 1 there in the denominator, minus 1 plus 3 squared. So this is 1/4. You get A is equal to 1/4. Pretty cool. So this method always works, and it's fast when you get used to it. So now I've got all of the constants here, so I'm going to put them in. A we just found is 1/4, right? And then we have B. B we found to be 1/2 earlier. That was easy. And C was easy as well. C we found earlier was negative 1/4. Okay, so now this is our expanded output spectrum, Y. Okay, so I'm going to erase some of this work. Feel free to pause the video, let it all soak in, right? And now, with an expanded Y spectrum, we can use linearity to consider each piece separately and forget about the constants, and then we can apply this common Fourier transform pair. So now, if I take each piece separately and take the inverse transform, we have 1/4 times the transform of this, which is, or the inverse transform of that, which is e to the negative t u of t. Then, let's forget about this term for a second. Let's move on to the third term. This would be minus 1/4 e to the minus 3t u of t. And then the second term, I'll write it out here. We did this in an example video. We have to use a new transform pair because of the square. T, e to the negative at u of t, has a Fourier transform 1 over j omega plus a squared. We did that. We used the differentiation and frequency property to figure that one out in a previous video. But that's in your table. That's in a table, and we've already done it. So now this is 1/2 t e to the negative t u of t. Pretty neat, right? Remember that that square in the denominator leads to a multiplication of t in time. All right, so we could, if we wanted to, work this out a little bit. We could factor out a half and a u of t from everything, and so this would be 1/2 e to the negative t minus 1/2 e to the minus 3t, and then plus t e to the negative t, all times the unit step, and that's the answer. That's what we get out. So let me summarize. We started with a differential equation. Here's our differential equation, and we're saying that characterizes a linear time invariant system. From this, we are able to find the frequency response and the impulse response. Then from the frequency response and some properties, we are able to get the output given an input. Here's the input. Okay, that's the engineering. So we were able to analyze this circuit or this mechanical system without even doing circuit analysis or vibration analysis or anything like that. Now, strictly speaking, in a mathematical sense, we were given a differential equation, something that relates x and its derivatives with y and its derivatives. Then we were given an x, and we solved the differential equation. Here's the answer: y of t equals this. So we solved the differential equation, and the reason, because you can do that, is exactly the reason you study these things in differential equations class. All right, so I think I've got one more video in continuous time Fourier transform. We're going to work on block diagrams and how the frequency responses change if you cascade different systems or you put systems in parallel. What happens to the frequency responses in this case? So I'll see you in the next video.